Hello, my name is Elizabeth Williamson, and this is Lab 5, the Slinky Drop. For this lab, we got to choose our own adventure, and I chose to examine the Slinky Drop and why it falls the way it does. We were to input a video into Tracker in order to interpret the data, and then input code into GlowScript in order to model the movement of the Slinky. We were also to determine if our model Slinky stays stationary at the bottom as it does in the video and determine why it does this. For this lab, we utilized a variation of Newton's second law, where F net equals the weight force plus the tension force before the bottom of the slinky begins to fall, and the weight force plus drag force after the bottom of the slinky begins to fall. During the first portion of the model, the tension force and the weight force, or gravitational force, are equal to each other, which is why the bottom of the slinky is held up. During the second portion of the model, the change in tension registers with the bottom of the slinky, so the slinky falls downward, meaning that the drag force is now equal to B, the drag constant, times velocity squared times j hat. We also utilized the velocity and position update formulas in this lab. The initial velocity was 0 as the slinky begins from rest, with V final equaling V initial plus F net over mass times delta t. The initial position was negative 0.0017 as determined from the tracker data, with R final equaling R initial plus average velocity times the change in time. Here is the tracker video with the point mass data illustrated along the y-axis. The distance that the slinky fell was calibrated using the height of the man on the right, which was found to be around 5'10" or 1.778 meters. Position data was recorded from when the slinky was first dropped to when it first hit the ground. All of this information was then used to code the model in GlowScript. The mass of the slinky was input at 0.9 kilograms, as this is the average weight of a slinky. The initial position data was then changed as well as the size of each time step, as the video was recorded at 300 frames per second. In the first while loop, up until 0.563 seconds, the slinky is stationary as discussed earlier, with the gravitational and tension forces canceling each other out. In the second while loop, up until the slinky touches the ground at 0.840 seconds, the slinky's bottom begins to fall with the rest of the slinky, so the gravitational force is larger than the drag force, which would equal 0 in this case, as the drag constant is also 0. Here is a video of the GlowScript model in action. As you can see, up until 0.563 seconds, the model is stationary, answering the question stated at the beginning of the lab. After this, the ball begins to fall due to the weight, or gravitational force, with the speed increasing until the slinky hits the ground. This is the comparison model of the observed data from Tracker and the computational data from GlowScript. As you can see, the observed data is a lot more jagged than the predicted data. This is most likely due to human error when tracking the video, the quality of said video, and also possible human error or external forces occurring when the video was initially recorded that are not being taken into consideration, though they both do begin to drop at the same time and follow the same general path of movement, with some deviation, of course. This properly illustrates, though, the slinky's movement when dropping to the ground and how it stays stationary until the tension begins to catch up with the bottom of the slinky. Thanks.